as supercharging becomes a standard feature for new energy vehicles, the heat generation issues of power batteries have been significantly magnified. For cylindrical cells, high C-rate charging and discharging led to rapid temperature rises and concentrated heat accumulation. Traditional bottom cooling often fails to dissipate heat quickly enough. Consequently, the industry increasingly favors side liquid cooling, where cooling channels are placed close to the sidewalls. In side cooling designs, a point that is often underestimated but has the greatest impact on performance is how the width of the liquid cooling flat tube matches the axial height of the cell. Let us first clarify the geometric relationship. The cell diameter mainly affects the bending radius and layout space of the serpentine tube, but the more critical factor is the width of the flat tube. The reason we emphasize that width must align with cell height is not to pursue full coverage for the sake of appearance, but to find a mass-producible balance point between heat dissipation efficiency and electrical safety standards. From a thermal perspective, the logic is intuitive. Cylindrical cells primarily transfer heat through their sidewalls. The wider the flat tube, the larger the contact area, the more thoroughly heat is removed, and local hotspots are more easily suppressed. When the flat tube is too narrow, thermal blind spots tend to form at the top and bottom ends of the cell, leading to significant temperature differences in the Z direction. If such temperature differences persist, they accelerate aging, widen consistency gaps between cells, and even cause the BMS to trigger current limits earlier. Therefore, thermal design aims to expand effective coverage as much as possible to ensure uniform temperature for individual cells. However, engineering cannot focus solely on heat dissipation. The top and bottom ends of the cell are the pole regions, which require space for installing bus bars, routing sampling lines, and allowing operation room for processes like laser welding. If we were to aggressively widen the flat tube to eliminate these minor thermal gradients at the ends, thereby encroaching upon the poles, it would not only obstruct assembly paths but also violate the critical red lines for creepage distance and clearance. This would introduce a fatal latent risk of high-voltage short circuits. Therefore, a mature side liquid cooling solution typically begins by defining the no-go zones dictated by safety standards and manufacturing constraints. On this basis, we determine the appropriate tube width by evaluating the target heat exchange capacity, estimating the effective contact area, and integrating coolant flow rates with production process capabilities. This process operates within the allowable window. Through calculations, prototyping, and testing, we maximize the flat tube's effective coverage to minimize thermal gradients in the Z direction. You can visualize this as first reserving a safety boundary for the poles and then filling the central region with the flat tube. In other words, the flat tube width is not simply the wider the better, but rather as wide as possible within safe limits. The ultimate goal is to ensure a balanced temperature for every cell under supercharging conditions, thereby securing both safety and longevity, making the system significantly more reliable.